Hello, welcome to this presentation on harmonics in electric power systems, a techno-commercial overview. In this part 1, we will see the basics of harmonics. I am Dr. Valluvan, professor in the Department of ECE, Velalar College of Engineering and Technology. I am working in the field of measurement of harmonics from the year 2005. The agenda for this presentation is why mitigating harmonics is so vital, what are the adverse effects of harmonics, what is the nature of linear and non-linear electrical loads, how do the voltage and current waveforms in loads appear, how harmonics are produced in non-linear loads, why do we use static power converters if they are the largest non-linear loads producing harmonics, and what are the standards for harmonic limits? Why mitigating harmonics is so vital in the present scenario? Due to the increasing number of nonlinear loads connected to electric power systems, the levels of current harmonics and therefore voltage harmonics are increasing. Harmonics badly affect the electrical equipment in the installation where the consumer's nonlinear loads are generating the harmonics, the utility grid supplying power to the consumers, and the other consumers connected in the grid. What are the adverse effects of harmonics? There are many. They produce distortion in supply voltage waveform. Due to the high frequency components, they cause overloading, overheating, reduced life, and probable premature failure of the transformers supplying power to the installation. Due to a concept called triple N harmonics, they cause overheating, probable puncture of UG power cables. Ideally, in a UG power cable distribution system where 3.5 core is practiced, the neutral conductor is will not carry any current. But if harmonics are present, there will be a significant amount of current in the neutral conductor which causes more heating and probably the UG power cable punctures. Increased voltage between neutral and ground conductors, which otherwise ideally should have been zero, are very minimal. Reduced current carrying capacity of the conductors, higher hysteresis losses in motors and transformers, inaccurate energy meter readings, reduced power factor, premature failure of power factor correction capacitors. Due to the negative torque generated, cracks in motor rotor shafts, malfunctioning of protective relays, nuisance breaker tripping, interference in communication lines, inefficient distribution system, higher operation and maintenance costs. In summary, the overall revenue losses caused by harmonics are very high. We can categorize the electrical loads into linear loads and non-linear loads. In linear loads, the supply voltage is sinusoidal and the current drawn by the load is also sinusoidal. In non-linear loads, the supply voltage is sinusoidal but the current drawn by the load is not sinusoidal. These are shown in the figures below. In a linear load, the supply voltage is sinusoidal. The current drawn by the load is also sinusoidal. In a nonlinear load, the supply voltage is sinusoidal, but the current drawn by the load is not sinusoidal. The linear loads have the nature of resistive, inductive, capacitive, or a combination of these three. Incandescent lamps and resistive heaters are examples for resistive loads. In resistive loads, when we apply a sinusoidal voltage, the current drawn by the load is also sinusoidal. Motors and transformers are examples for inductive loads. In these loads, when we apply a sinusoidal voltage, the current drawn by them is also sinusoidal, but the current is lagging behind the voltage. Power factor correction capacitors are examples for capacitive loads. When we apply a sinusoidal voltage to them, the current drawn by the capacitive load is also sinusoidal, but the current is leading the voltage. The lagging current in an inductor and the leading current in a capacitor cause the phenomena of power factor. There are several categories of non-linear loads. Static power converters, arc discharge devices, saturated magnetic devices are all non-linear loads. Variable frequency drives and DC drives, which are generically known as adjustable speed drives, uninterruptible power supply and SMPS, EV chargers and induction furnaces belong to static power converters. Welding equipment and arc furnaces belong to the category of arc discharge devices. The static power converters are the largest non-linear loads in use today. Rotating machines to a lesser degree also produce harmonic currents. So, what are harmonics? A periodic, distorted, that is non-sinusoidal waveform of frequency f can be resolved into a sum of one sine wave of the same frequency f called the fundamental and many other sine waves whose frequencies are integer multiples of the fundamental, that is 2f, 3f, 4f, etc. These components other than the fundamental are called harmonics. In a 50 Hz power system, fundamental has the frequency of 50 Hz, harmonics have frequencies of 100 Hz, 150 Hz, 200 Hz, etc. Theoretically, they can go to a large number, up to infinity. The numbers 2, 3, 4 are called the order of harmonics. Pure sine wave has no distortion, so it has only fundamental and no harmonic. How do we resolve a distorted wave into many sinusoidal waves? This distorted waveform, which is non-sinusoidal, has a frequency of f. This represents the load current drawn by the nonlinear load in a variable frequency drive. This is resolved into one fundamental with the same frequency f, another waveform with 2 times the frequency of f, yet another waveform with a 3 times frequency 3f, another waveform with 4 times the frequency, and so on. Theoretically, this resolution can go up to infinity number, but for most practical purposes of measurement and mitigation, these are limited to either 40th order or 50th order. The fundamental and harmonics are graphically shown in a column chart. Fundamental is shown as 100%. Harmonics are shown as ratios of the fundamental in percentage as in the diagram below. We have a sine wave which represents the supply voltage. This is resolved, and since it is pure sine wave, it has only fundamental component. The load current, which is distorted when it is resolved, has many components, namely the fundamental, second order, third order, fourth order, etc. The current harmonics distort the shape of the supply voltage from a sine wave to a non-sinusoidal wave, which can be explained in a diagram like this. We have a generator generating sine wave voltage, which supplies through a transmission line to a substation. From the substation, the power is transmitted to the consumer's transformer. The consumer's transformer supplies non-linear loads which take the load current in non-sinusoidal form. This distorted current distorts the voltage waveform, and this distorted voltage wave is applied to the other consumers. We saw static power converters convert AC to DC called rectifiers, DC to DC called choppers, DC to AC called inverters, and AC to AC called cycloconverters using power electronic circuits. In many equipment, these four topologies are used individually or in a combination. When static power converters are non-linear and they produce current harmonics, why do we use them? The static power converters provide energy savings, which is the largest benefit of them. They are very accurate to control. There is a possibility of remote operation. They are compact in size and less weight. They offer better reliability. Standards refer to two indices for measuring harmonics, namely total harmonic distortion, abbreviated as THD, total demand distortion, TDD. Total harmonic distortion in voltage is the ratio of the root mean square of the harmonic content considering harmonic components up to the 50th order and specifically excluding interharmonics expressed as a percentage of the fundamental. THD is equal to square root of V2 square plus V3 square plus V4 square etc. up to V50th square divided by V1 into 100%, where V1 is the fundamental voltage component and V2, V3, V4 up to V50 are the voltage harmonics up to 50th order. Total demand distortion in the current is the ratio of the root mean square of the harmonic content considering harmonic components up to the 50th order and specifically excluding interharmonics expressed as a percentage of maximum demand current. TDD is equal to square root of I2 square plus I3 square plus I4 square plus up to I50th square divided by IL multiplied by 100%, where IL is the maximum demand load current and I2, I3, I4 up to I50 are the current harmonics up to 50th order. The most widely referred and followed standard globally is the IEEE 519 standard for harmonics limits. IEEE standard 519 2022 is the latest version of this standard, which is titled as IEEE standard for harmonic control in electric power systems. The scope of this standard is this standard establishes goals for the design of electrical systems that include both linear and nonlinear loads. The voltage and current waveforms that may exist throughout the system are described, and waveform distortion goals for the system designer are established. The interface between sources and loads is described as the point of common coupling (PCC), and observance of the design goals will reduce interference between electrical equipment. As per the IEEE standard 519, the voltage distortion limits are given in this table. At the point of common coupling, system owners or operators shall limit line to neutral voltage harmonics as follows. These limits are based on the bus voltage at the PCC. The standard also gives the current distortion limits for many PCC voltages. So this table is for the PCC voltage of 120 to 69 kV. These values are based on a parameter called short circuit ratio, which is ISC divided by IL. Central Electricity Authority of India published standards for harmonic controls in the year 2007, 2013 and 2019. Those standards, Tamil Nadu Electricity Regulatory Commission published amendments to the Tamil Nadu Electricity Supply Code on current harmonic control and notified in Tamil Nadu Government Gazette dated 21/9/2022. The salient points of TNERC notification are: measurement of harmonics shall be made at the PCC point of common coupling of the installation. Power quality meters complying with IEC standard 61000-4-30 edition 3 class A shall be used for measurement. The licensee shall use his portable power quality meter for 1 week for each installation. If the measured values exceed the limits, a notice shall be issued to the consumer to install harmonic filters within 6 months. The notice shall also convey that in the case of non-compliance, penalty will be levied by the licensee for the subsequent 12 months. In case of non-compliance, even after the 12 months, supply to the service shall be disconnected. The penalty for excess TDD is given in this table. A penalty of maximum 10% in steps of 1% increase will be levied on the monthly current consumption charges up to 3% in excess of the limits. The penalty is 1%. Up to 6%, the penalty is 2%. Up to 9%, the penalty is 3%, and so on. So, the maximum penalty is 10%. In part 2 and part 3 of this sequence, we will see the standards for harmonic control and the associated IEC standards, measurement methodology in detail. A brief about myself. I worked in industries like ABB for 11 years and teaching for the past 27 years. Carried out harmonic studies in various HT and EHT industries at the request of TNEB in 2005. Received PhD from Anna University in 2009 for the thesis Implementation of Adaline on DSP and FPGA for Measurement of Harmonics. I have been delivering presentations on harmonics and their ill effects to TNERC, TNEB, industries and institutions from 2005. Along with senior consultant Dr. A.S. Kandasamy, I submitted 2 consultancy papers on harmonic control, one for HT industries and 2 for inverter-based resources, distributed generation resources to TNERC. Our collective endeavor is to make the distortion-free, that is non-sinusoidal current waveforms to a sinusoidal waveform. Thank you very much for watching this video.